This is Design Project 3 by GroupA14, Tom Simonson, Aubrey Bradford, A.V. Schilt, Aaron Whitehouse, and R.J. Scavo. The objective of this project was to take an input of 2.5 horsepower at 800 RPM and use a gearbox to reduce that speed to 20 with a range of 10 either way RPM and increase the torque to 7,750 with a range of 500 either way pounds force inches. The parameters that we were given for the gearbox is the maximum center to center distance of the input and output shafts is to be 6 inches. There's to be a 0.375 inch clearance around gears in all directions. Maximum gear ratio that we can have is 10:1. And we can change the pressure angle, the diametral pitch, the size, the number of teeth, and the material of the gears. The process we took was first to find the total reduction ratio needed to achieve the required output speed. Then with that, we decided on how many shafts we would need to reach this reduction, which in turn will affect the amount of gears we needed. Then we determined the gear ratio for each shaft. And based upon that, we chose the pinion and gear for the first reduction. We tested them for interference, and then we repeated this for each further reduction. After we had a solution, first thing was to test the RPM and see if the output RPM was within the specified range. Then we tested the output torque to see if that torque was within that range. And then after we had the RPM and torque within the desired ranges, we would test the failure criteria for each gear using the Barth revision of the Lewis formula to see if any of the gears fail. And if any of the criteria wouldn't be met, we iterated and went back and started to try and improve on the solution, and the final solution took around 50 iterations to complete.
First, starting out with the calculations, we just wanted to do all the givens and initially find if our gear ratios would in fact work with the given parameters for the speed. So first off, we went in order for the gears and labeled them 2 through 7 to have a total of 6 gears. And when it came out, we got an RPM that fit within the range of 20.455 revolutions per minute. To check the interference for the gears, we decided to have a max gear ratio of 6, since none of ours actually went that high. And with the given calculations, we found that a 16 tooth minimum was required, which we surpassed with everything being above 16. To find the torque calculations, you first had to find velocity for each given shaft on each, for each gear on each shaft. And then it was necessary to find the work that was found on each gear in order to first show off what that would be to help in the next set of calculations, as well as further down the line when we had to find all the interference loads as well. And as you can see on the bottom, our final torque on the last gear fits within the range of having it being 7,703 pound force per inches. For the Barth revision of the Lewis equation, we had to put in a few variables, which we did with materials of either cast iron or steel. And with the steel, it wasn't given specifically. So we went with the 0.2 carbon case hardened, since it seemed like the best fit for the type of gears we had. And then for the number of teeth, we went with a 20-degree angle and full depth, since that was given to us in the assumptions. For the Barth-Lewis equation, you can see that most of the velocities for each gear on each shaft would have been the same, so that is why there's only 3 really given. And then each of the face widths were mainly the same, and that's what is the y variable. And then for the given teeth, it was just changed based on which gear we were looking at. And so finally, to look to see if all of our equations worked, we put on the left side what the actual gear force would have been compared to what the Lewis equation said its maximum could be. And since they never overshot the maximum, it worked in the end.
The first gear in the gear train is the YJ27A model from Boston Gears. This is a spur gear with a diametral pitch of 6 and a pressure angle of 20 degrees. On this gear, there are 27 teeth. The pitch diameter is 4.5 inches, and the material is steel. The second gear in the gear train is the YJ120B model from Boston Gears. This is also spur gear with a diametral pitch of 6 and a pressure angle of 20. On this, there are 120 teeth. It is a cast iron gear, and the diametral pitch, or the pitch diameter, is 20 inches. The third gear in the gear train is the YJ30C from Boston Gears. This is a spur gear with a diametral pitch of 6 and a pressure angle of 20. There are 30 teeth on it. It has a pitch diameter of 5 inches, and the material is steel. The fourth gear was also the YJ120B, and just like the first, it has 120 teeth, diametral pitch of, or pitch diameter of 20, and material is cast iron. The fifth gear is also the same as the third gear. This is a spur gear with the diametral pitch of 6 and a pressure angle of 20, 30 teeth, pitch diameter of 5 inches, and the material is steel. The final gear, the sixth gear in the gear train, was a YJ66B model from Boston Gear. There's also a 6 spur gear with diametral pitch of 6 and a pressure angle of 20. On this, there are 66 teeth. It has a pitch diameter of 11 inches, and the material is cast iron.
The 6 gears fit in a close-fitting casing made out of cast iron with a minimum wall thickness of 1/2 inch. The general shape of the casing is the overall silhouette of the gears themselves. The casing was made so that each gear has 3/8 of an inch of clearance on all sides, including between gears and between the gears and the shell. The assembly was made in 2 parts for easy assembly. The bottom shown on left and the top shown on right. Certain features like bearings, keyways, and other features were omitted from the design as they weren't the focus of this project. As seen on the lower casing assembly on the left, the input and output shafts both only go through half of the casing. A divider on the inside acts as a second support for both shafts. Both shafts on the upper casing assembly on the right extend fully through the casing. This is due to both shafts carrying 2 gears each.
When designing the GD&T for all these parts, the important call-out locations included surface interfaces, shaft interface locations, which will help keep any shafts parallel within the casing itself. Checking for the appropriate clearance when it comes to actually making the assemblies, as well as the input and output shaft total distance. No shaft drawings were included within this drawing packet, as those interfaces would be outside the scope of this project.
The last piece of this project was interface forces for each shaft. For the first shaft, as seen below, there is a bending moment diagram which shows our maximum bending moment, and a diagram on the left for our shaft and the forces on it. Below, you can see the calculations for maximum torque on the shaft, the forces on each bearing, and the maximum bending moment.
So the interface forces on shafts 2 and 3, there's absolutely no radial loads imparted on those idling gears. So there's no radial loads on the shaft or the bearings. The maximum torque on shaft 2 is equal to TB, and the maximum torque on shaft 3 is equal to TC.
Similar to the interface forces on shaft 1, we have provided a bending moment diagram as well as a free body diagram of all the forces that would be involved. And as you can see, the calculations below indicate in order the maximum torque that would be on the final shaft, the two forces that would act on the bearings, and then finally the bending moment that was given from the graph on the previous page.